All right, guys, let's start. So now we are focusing on your next chapter, which is your random variables, right? Fundamentals of probability. Still, we are doing chapter number one. We are doing lesson number two, which is random variables, right? See, in this particular chapter, what is important to understand, the chapter is one of the most important chapters in all of quant finance, right? If someone asks you what is a single mathematical idea behind your option pricing, your war, your Monte Carlo simulations, your Black-Scholes, your stochastic calculus, your machine learning in finance and risk management, the answer is random variable. Everything in quant finance begins here. Okay. So let's go deeper, guys. Let's try to understand. Now, in the first slide, right, we are trying to do your introduction to your random variables. The first slide, please try to understand, right? We're trying to understand random variable, turning outcome into numbers. We're talking about your, what do you say, very, very fundamental things, right? So, okay, this particular lesson, right, is a bridge between your probability theory, your statistics, your stochastic process, uh, quantitative finance, etc. Right? Before this chapter, right? Okay, our thinking was very, very deterministic in nature, right? So we always thought about your probability, your statistics, right? In a very deterministic manner, right? As we studied in the school, right? Now here, right? Here in this particular chapter, we are now getting into a probabilistic kind of thinking, right? What's a probabilistic kind of thinking? Basically, we are thinking in terms of your uh, random variables or distributions, right? So that's how our thinking is evolving, right? And again, you know, this is a kind of topic which where we're focusing on how do we convert your uncertain outcomes into number, which is very, very essential if you want to understand your quantitative finance model, right? So that is what we are trying to do, and that's the whole idea we are trying to develop here, right? So keep that in mind, right? So random variable is nothing but a numerical output of a random experiment. A random variable x is a function that maps each outcome in the sample space S to a real number, right? So we studied what is your sample space, right, in the previous chapter. Now we are saying that a random variable x is a function that maps each outcome in the sample space, right, into your to a real number, right? That's what we are trying to do. Okay. Now the variable, what we are trying to do, right? If you look at it, why random variables matter in finance? Because financial markets contain uncertainty, asset prices, return, interest rate evolve randomly. Risk management requires measuring your uncertainty numerically, right? So imagine like tossing a coin, sample space is heads and tails. A random variable converts outcome into number. For example, we understand that there are two outputs, so we kind of know that it's a binomial distribution, right? So instead of working with heads and tails, we work with numbers in your binomial distributions, or mathematics can begin now, right? And why finance needs random variables? I have told you, right? Financial markets are uncertain. Nobody knows tomorrow's stock price, tomorrow's return, tomorrow's interest rate, tomorrow's volatility. Therefore, we need distributions, right? That's what we are trying to do understand here, right? Finance example, ST is the stock price at time T, RT is the return of an asset over time T, and small RT is the short-term interest rate stochastic. Key takeaway, random variables contain uncertain outcomes into number and ending quantitative finance models that we need to understand very, very clearly. Model interest rate models treat rates as random. Example, Vasicek, CIR, Halvite, all assume we follow a stochastic process. Uh, Even in Black-Scholes, we understand that it's not a fixed number, it's a random variable. Later it becomes the entire equation, stochastic equation. The entire stochastic differential equation is built on the idea introduced in this particular slide, right? So that's what we are talking about here. Now, next one is we are trying to understand your discrete random variables. A discrete random variable takes a countable set of distinct values. Example, coin flip that x is equal to number of heads in three coin flip x, x has three coin tosses, right? So the value could only be number of heads we are trying to find is 0, 1 to 3, right? Finance example, discrete number of defaults in a credit portfolio, number of extreme losses in a days, in a month, number of trades executed in a minute, which is about market microstructure, right? And similarly, discrete variables are modeled using your probability mass function, Px is equal to x. The key takeaway here is discrete random variables count outcomes and are used to model events like defaults, crashes, or occurrences, right? So the idea is that whether we are talking about number of heads, whether you're talking about number of defaults, uh, in heads, only 4 values are possible. In number of defaults, suppose portfolio contains 100 companies, right? Similarly, number of crash days, we can calculate number of trades, high frequency trading, trades per second, we can calculate. Discrete random variables count your outcomes and are used to model events like default, crashes, occurrence, right? Uh, we also need to understand something called your probability mass function, right? Which helps us to uh, model this. Discrete variables are modeled using your probability mass function, right? It's a mass function, right? Meaning we are trying to give a particular percentage chance for each thing, right? For example, mass functions, probability mass function tells you probability that x is equal to x, right? So if I tell you that uh, probability of x is equal to 3, right? So it is like probability, and I tell you that probability x is equal to 3 is equal to 15%, right? If I tell you probability x is equal to 3 is equal to 15%, what does it mean? It means that 15% chance of exactly 3 defaults, right? Why do we need to study this? Because if you try to join the dots in the quant, when you're looking at credit risk, default models often begin as discrete random variables, operational risk, number of fraud events, market microstructure, trade arrivals, all use discrete random variables we need to understand, right? So very, very, very important in this context, right? Then we get into the continuous random variable, another category. The continuous random variable can take any value in a continuous range. For example, let ST be the stock price at time t. ST can have any value from 0 to 1000. Finance example, asset returns, interest rate, volatility, portfolio values, right? Continuous variables are described using probability density function. That was a mass function, it's a density function. It is different, the formula is different. Goals in quant finance, quantified uncertainty, price derivatives. Again, a continuous random variable can take infinite values. For returns, it is used interest rate, volatility, portfolio volatility. And why continuous model dominate quant finance? Because real markets move continuously. Therefore, model becomes continuous rather than discrete. Probability density function, the formula is in front of you. Integral of fxx dx from A to B. This formula will appear everywhere from Black-Scholes, Monte Carlo, war, expected shortfall, portfolio theory, everywhere. So we need to understand that. Okay. Once we have done this, we get into next part, which is discrete random variables and the uh, PMF. A discrete random variable takes only a finite or countably infinite set of discrete values. These values are typically integers or counts. Example, discrete outcomes, number of heads in 5-coin toss, number of defaults in a credit portfolio, number of days, stock close, positive in a month. Probability mass function, a PMF gives the probability that a discrete random variable equals a specific value, right? Basic PMF properties, this and this, basically value lies between 0 and 1. And the summation of the value is equal to 1, right? The key takeaway, discrete random variables are modeled using a PMF probability mass function, which assigns probability to each countable outcome, right? So understand these properties. Probabilities cannot be negative. That is one part. Total probability must equal 1. That's another one. This is one of the most important mathematical constraint in your probability. Why? Because one of the outcomes must happen, right? Uh, we need to understand that, right? So that's very, very important. Okay. So keep that in mind, guys. Very, very important when you try to understand uh, this particular kind of lesson, right? So discrete random variables are modeled using a probability mass function, which assigns probability to each countable outcome, right? We assign probability to each countable outcome, right? So we need to understand that. Fine. So remember that, guys. Okay. Now, once this is done, we move to the next part, which is PM, for example, fair six-sided die, let X be the outcome of a fair six-sided die. So obviously the possibilities are 1, 2, 3, 4, 5, 6. The PMF, the probability mass function of a fair die, Px is equal to X, right? What's the probability out of 1 out of 6, right? 1 by 6. And X is equal to 1, 2, 3, 4, 5, 6, meaning every outcome is equally likely, probabilities are evenly distributed across all integers in the sample space. Now, please understand, how do we check the properties also? The probability of X is equal to X is equal to 1 by 6. And when we do it for all of them, X is summation 6 into 1 by 6, it makes equal to 1. So that checks our understanding, right? That is what we wanted to understand very, very clearly, right? So this is totally fine, right? And a fair die is the simplest of your PMF example. Each discrete outcome has a probability of 1 by 6, right? So that's totally fine, right? Because we are getting a simple kind of validation, right? Valid PMF, right? So that is what we are getting, right? So that's totally fine. Okay. So that's what we understand. And why this matters? Because the die is the simplest version of your binomial tree. Okay. And binomial tree can be used in option pricing also. We can use SU is equal to US, right? And SD, right, is equal to your DS. Right, U and D are your up move and down move factor. Instead of 6 outcomes, you have 2 outcomes. The idea is very identical we use in your binomial tree option pricing models, right? So that is what we need to understand. Okay. So keep that in mind, guys. Pretty basic stuff till now. Next one is binomial random variable success counts, right? Again, the slide is extremely important. A binomial random variable count successes definition X, right? X is your binomial n comma p, where n is trial, p success probability. Financial interpretation here is that trial 1 trading day success stock goes up, random variable number of updates. Suppose n is equal to 10, p is equal to 0.6, text count, update 10 days, possible value 0, 1, 2, 10. Why binomial matters here is because the foundation of a lot of models, right? Like CRR model, the famous binomial option pricing model we have, where SU is equal to US and SD is equal to DS. The entire model comes from the binomial random variable, right? So that is very, very important, right? SU is equal to US and SD and DS. Up move, U and D are up move and down move factor. The entire model comes from your binomial random variable, right? And modeling discrete up down moves in the stock prices. One model converts market movement into a discrete count of successes across time steps. I told you in the previous one also. A binomial random variable counts the number of successes and independent trials. Trial is equal to 1 trading day. Successful stock goes up. X is equal to number of updates. And each trial has the same success probability. Trials are kind of independent. And this is what we get. Then next part is your binomial distribution, PMF, and parameters. Okay. Now, if X is a binomial distribution, the next counts the number of successes in n trials. Right, binomial PMF is given like this formula. Right, K is equal to 0.1 to n, where this is like NCR, right? This is the combination, guys, right? So in school day, you must have heard of combination, right? This is a combination, right? N factorial divided by K factorial divided n minus K factorial is the binomial coefficient, right? P is the probability of success in one trial. K is the number of successes. T is the number of trials. Financial meaning. N number of trading days or binomial time step. K is number of up moves. P is the probability of an up move per step. The key takeaway: the binomial distribution is a core discrete model used in early option pricing and success counting modeling. Same idea. PK. If I say P raised to power K, right? PK is basically you need K successes, right? So that is what it is, right? 1 minus P, N minus K need the remaining failures, right? So let's say we have 10 trading days, N equal to 10, probability of stock rise is 0.6, right? So find probability of exactly 7 updates, right? So what are we asking here? right? We are asking here, your pk will become 0.6 raised to power 7. Your 1 minus p n minus k, right? 1 minus p n minus k will become your 0.4 raised to power 3, right? And ultimately, what you are doing is what, right? So it is your 10 uh, 7, right? So it's NCR, right? N7 combination and zero point 0.6 raised to power 7, zero point 0.4 raised to power 3. Okay. So ultimately the answer is 120 into 0.02799 into 0.064 equal to 0.215, right? Which is 21.5%, right? So please understand when you're talking about CRR, binomial tree, up and down movement as n tends to infinity, binomial distribution converges to normal distribution. And then normal distribution leads towards your Black-Scholes. Is one of the most beautiful transition in quant finance, binomial to normal to Brownian motion to Black-Scholes that we need to understand. Okay. Once this is done, then we have continuous random variables and the PDF. A continuous random variable can take any real value within a continuous range. Key feature, it does not assign probability into a single point. Different probabilities are assigned to intervals, probability density function we have. PDF fx describes the relative likelihood around values of x. Bound properties, fx, x greater than or equal to 0, and integral of fx x dx from minus infinity to infinity is 1, right? Key takeaway, continuous uncertainty is represented using densities, not point probabilities. We move from PMF to PDF, discrete. You have which is Px is equal to x, continuous fxx. The key difference, discrete, probability assigned directly, continuous density assigned. The properties fxx greater than or equal to 0, right? Uh, and the other one, the second condition is basically, right, the continuous equivalent of, this is the continuous equivalent of your, which you saw earlier, right? Okay. So it is the continuous equivalent of summation probability of x equal to 1. So remember that, right? So PDF of x describes the relative likelihood around values of x. Okay. So that is what we have. Then we get into the next part, which is probabilities come from areas under the PDF. Right, for continuous random variable x, the probability that x lies in an interval so and so. Right. The key point here is Px is equal to x is equal to 0 for any single value x. Because a single point has 0 area under a curve. The financial intuition here is returns are measured continuously, risk is evaluated over ranges, tail intervals, pricing, user expectations, right? You need to keep in mind. The slide contains one of the deepest idea in your quantitative finance, probability area, not height, area, probability between two values are already been given. Right, why a single point has no width, therefore Px is equal to x equal to 0 for any specific x. For example, Px is equal to 100 is also 0, right? Even though stock price might actually become 100. This confuses many students because people don't understand or grasp this properly. A point has 0 area, right? That's why this Px equal to x is 0. Quant finance interpretation, when calculating your value at risk, let's say VAR 95%, we compute area in the left tail. When pricing option, expected payoff, again, we are trying to calculate the payoff of x, fx dx, again area. When doing Monte Carlo, we are approximating these integrals numerically. The big picture so far, right, what you have studied is that this entire chapter till now, slide number 1 to 10, right, is building the foundation for x can be a PMF, probability mass function, or PDF. Then PMF, PDF will lead to your expected value, then expected value will lead to pricing, then pricing will lead to Black-Scholes, and Black-Scholes will lead to modern quant finance, right? So far, you have essentially learned the language that every stochastic model, your option pricing, your risk model, Monte Carlo engine speaks. The next major concepts will typically be CDFs, your expectation, variance, uh, moments, and distribution, which are the engines that turn random variables into actionable financial decisions, right? So that's what we do, right? Okay. Now, with that, we move to the next part. Next one is now we try to understand the normal distribution, the most important distribution in your quant finance. We need to understand. Okay, so very, very, very important, right? So keep that in mind. Okay, see, when we talk about your normal distribution, right? Normal distribution is widely used in your financial modeling for returns and your errors, right? Uh, so we say that X follows a normal distribution where n mu sigma square mu is the mean, sigma square is the variance. And then we are giving its PDF, probability density function. See the formula, fx x is equal to 1 by sigma under root 2 pi exponential minus x minus mu square divided by 2 sigma square, right? Where mu is the mean location of distribution, sigma square is the variance spread of the race, x is the value of the random variable. What is the finance linkage here? Please understand. Short horizon returns are often approximately normal. War and risk models frequently start from your normal assumptions. And as I told you, mu is the mean location of the distribution. Sigma square is the variance, spread of risk, S is the value of the random variable. The key takeaway is the normal PDF provides a smooth continuous density with parameters mu and sigma square controlling your location and risk that we need to understand. And the normal PDF provides a smooth continuous density with parameters mu and sigma square controlling your location and risk, right? Very important to understand, right? So ultimately, everywhere, whatever distribution you take, right, you have to define it with certain parameters, right? In this parameters, there are two things. One is mu sigma square. Mu is about location, right? Sigma square is about your risk, right? So we need to understand both to understand how a distribution will shape up, right? This is very, very important. And as given the slide, in finance, whenever we are looking at your short horizon returns, right, they are often approximated as normal because normal distribution, obviously, it's easier to understand a lot of properties, which kind of helps us easier to understand. And X is the value of the random variable, which also plays a very vital role, right? So please understand that. Okay. So overall, this slide is arguably the foundation of your modern quantitative finance. X follows the normal distribution mean mu and variance sigma square. Why the normal distribution is so important? Because imagine you're collecting daily returns of a stock, you might observe -2%, 1%, 0.5%. Your minus 1.5%, 2.1%. Plot 1,000 of each observation, you often get a bell-shaped curve. This is the famous Gaussian distribution. The PDF formula is given. You do not need to memorize every symbol. Immediately understand the role of each part. Mu controls the center. If mu is equal to 0, distribution is centered at 0. If mu is equal to 5, the entire curve shifts right. Variance sigma square controls the spreads. Sigma square is small variance, right? And sigma square is big, large variance. Finance interpretation, suppose n is 0.10, 0.2 square, meaning expected return is 10%, volatility 20%. This assumption is the starting point for War, Kaplan, Markowitz, Blackstone. And why quants love it? Because the normal distribution have beautiful mathematical properties. Sums of normals remain normal, integrals become tractable, derivatives can be priced analytically. Important reality checks here are that real markets are not perfectly normal. Markets have fat tails, skewness, crashes. Example 2008 crisis, normal models might say probability of loss greater than 10 sigma is nearly impossible. Reality says it happens. It leads to student T distribution, jump diffusion models, stochastic volatility models, etc. Right. So again, remember that I've given you a lot of context here to understand that. Okay. With that, we get into the next part. We try to understand log normal distribution and the stock prices, log normal model for the stock prices. Again, this is very important slide in finance. Stock price are modeled as continuous random variables, right? Why not normal for price? The normal distribution allows negative rates. Stock prices must satisfy this. Why not model stock price as normal? Because see, if I try to do in a normal way, possible outcomes can be 120 or 80 or -50 if I do n 150 square, right? Problem is stock prices cannot be negative, right? Fundamental requirement, stock price must satisfy ST greater than 0. Always stock price has to be greater than, instead of saying ST is normal, we assume LNST. right? LNST is normal, right? So that is what we assume. If LNST follows n mu sigma square, then S is normal by this work. Exponential are always positive. Ex is always greater than 0 for every x. Therefore, S is equal to Ex. Can never become negative. What is the connection to geometric ground motion here? The slide puts the formula dst is equal to mu st dt plus sigma st dwt. Right. Uh, Basic thing is, if you record it, mu st dt is the drift. Right. This is the drift part, expected growth. This is the random shock, uncertainty, Brownian motion. WT represents continuous random market shock. Massive quant insight here is that ST, when you solve this equation, right, ST is nothing but S naught exponential, right? In the bracket, we get mu minus your sigma square by 2 T, comma, sigma, right, WT, right? So since exponential appear ST must be log normal distributed, this is why Black-Scholes assume log normal stock prices. Under GBM, ST becomes log normally distributed. Why it matters in optional pricing? Black-Scholes assumes stock follow GBM, so prices remain positive and returns are continually distributed. Okay, so that is what we get. Fine. Then we get into the next part, which is CDF. CDF, the probability that X is below a certain threshold, right? Now we move from density to cumulative probability. Definition: fxx is equal to px less than equal to x, right? Meaning the probability of x is below x. For example, right, suppose returns are normally distributed. Question probability return is less than 5%. So probability of return of less than 5% is given as, how do you write it, right? If I have to write it in a particular way, how do I write it, right? So this works. Um okay, this is exactly your FR 0.05, right? So properties we understand. The value which we will always between 0 and 1, right? Non-decreasing as x increases, probability accumulation or accumulated increases, never decreases. Limit x with going to minus infinity, fx is x equal to 0. Limit of x tends to infinity, fx x equal to 1. Financial interpretation, risk manager constantly asks what is probability loss in less than 10 lakh? This is CDF question, right? And small x close to 0, large x close to 1. The CDF directly answer what is the probability that x is at most x, right? So cumulative distribution function measures the probability that a random variable x takes a value less than or equal to. That's what we have. Now, then we go into CDF for discrete random variable. Discrete case, CDF is cumulative sum of probabilities. The formula is given fx equal to this, right? This is given, for example, let's take a die. Pair die, probability of 1, 2, 3, 4, 5, 6 equal to 1 by 6. Probability of, let's say, find F3, right? Fx3, probability of x less than 3. So probability of 1 to 3, you add 1 by 6 plus 1 by 6 plus 1 by 6, 3 by 6 to 1 by 2. Right? So shape, discrete, CDF, looks like staircase kind of thing, right? Each jump equals the probability mass. The quant connection here is that get default count for Poisson arrivals, straight counts, all have step shape CDF, you need to understand, right? So shape of discrete CDF. It increases in jumps at discrete points. It has step-like function. Key takeaway: discrete CDF is computed by summing EMF values up to the threshold. Let X be the die outcome, right? So this is what we have, right? Then CDF for continuous random variables. For continuous random variables, the CDF is the integral of the PDF, right? So fxx, probability x less than equal to x is given this, x minus infinity fxt dt, right? Meaning CDF is accumulated area. Imagine you are kind of filling a bucket. PDF is the flow rate, right? CDF is like water accumulated. The slide is trying to connect the PDF and CDF. There is an interval probability also given. very important formula, which is probability of between A and B, right? Fx B minus Fx A. This formula appears everywhere. For example, let's say F3, right? F3 is equal to your 0.80, F1 is equal to 0.20, then probability of being between 1 and 3, right? 0.80 minus 0.20 is equal to 0.60, right? 0.60. Relationship with CDF is differential fxx is equal to d by dx of fx by fxx. PDF is derivative of CDF. CDF is integral of PDF. Finance connection, option pricing, integral CDF, risk management, tail probability CDF. Monte Carlo empirical CDF, we need to understand. Continuous CDF is the accumulated area under the PDF from minus x to minus infinity to x. Right, that's what we get. Then we get into why the CDF matters in finance with example curve. This slide finally explains why quants care so much, right? Black-Scholes, the famous formula is C is equal to your S naught and D1 minus K exponential RT and D2 contains ND, which is the standard normal CDF. What is ND? ND is nothing but your probability of your P. ND is what? ND is what? Probability of Z less than equal to D, right? Where Z lies between 0 and 1, right? So if N1, let's say, is given to you 0.8413, meaning 84.13 observations lie below one standard deviation, right? This is used for your risk management. Value at risk war 95 comes from F minus 1, 0.01, 0.05, which is inverse CDS, right? Tail probability, right, which is used, probability of large loss, probability of loss greater than 10 million becomes your, if I have the probability of loss greater than 10 million, it becomes your 1 minus F 10 million, right? So these are the applications. The option pricing we have, I gave you the formula, normal CDF, this is the value. If I gave you, this is what it is written, probability of loss, FX loss, I gave you. CDF converts distribution into their probability statement used in pricing effects, right? So we understand that. Then we get into expectations. Again, we now enter the heart of the pricing theory. Expectation is everything in quant finance. We need to understand definition of ES. Expectation is a long run average outcome. There's a casino example. For example, roll a die forever. Average outcome approaches expected value of X. Financial interpretation, in this case, right? Expected return, expected stock price, expected payoff, right? We have to keep in mind. Okay, so you can use it for anything, right? Why it matters? Because modern pricing says price is equal to present value of expected future cash flow, right? So everything comes down to expectation, right? So finance expected return is an asset, is the average return implied by probabilities used in portfolio construction decision making. Expectation increases the typical level of random variable, right? And repeating the experiment many times is the value we get, right? So expected value of random variable denoted EX, right? Then we get into the next part, which is your expected value for discrete random variable. If X is discrete random variable, PMF, PX is equal to XI, then expected value is this. Interpretation here is multiply each outcome value by its probability, add all weighted outcome. Example is simple discrete RV. Suppose X can take value 0, 1, 2 with probabilities, right, which is given 1.1. So what is happening here is we are taking the weighted average, not an ordinary average, probability weighted average. Example X is 0, 1, 2, probability is 0.2, 0.5, 0.3, 0 into 0.2, 1 into 0.5, 2 into 0.3, 1.1. Finance version, expected return is given. Expected return is this. This is exactly the formula behind the scenario analysis, which we need to know, right? Key takeaway, discrete expectation is the weighted average of outcomes. We need to understand. Okay. So that is what we have, and then we get into the next part. Expected value for continuous random variable, right? Simple idea. Here is okay. Uh, Fine. So keep understand that. So now your summation becomes your integration, nothing else, right? If x is continuous random variable, PDF x, fx equal fxx, then summation becomes your integration. Expected value is value of x fx x dx integral minus infinity to infinity. This is one of the most important formulas in quant finance. By option pricing, basically expected value of payoff under a risk neutral measure. Black-Scholes price is equal to minus ERT EQ payoff. This entire $1 trillion derivative industry comes from this idea. Monte Carlo simply estimate expected value of payoff numerically, nothing more, nothing less, right? So integral form of a weighted average. Weighted comes from the density fxx. And then please understand very clearly that finance example, continuous time returns under stochastic models, expected payoff pricing. The key takeaway, continuous expectation is computed by integrating across all possible values of x, right? Nothing more, nothing less. Monte Carlo simply estimates the expected payoff, right? Then we get into the next part, which is slide number 20. Expectation tell us your average outcome, variance tell us the uncertainty, right? Definition, if you look at variance of x, right? Expectation of x minus ex square, right? Equivalent form, very useful. Variance of x, ex square minus ex square. Interpretation, take deviation from mean, x minus ex, square them, average them. Y square without squaring, positive and negative derivations or positive and negative deviations will cancel. Right. So very important, variance of x is equal to ex square minus ex whole square. Quants use this constantly because it is computationally easier. Standard deviation is given, right? It is under root of variance x. Financial interpreted Finance interpretation, volatility sigma is simple standard deviation of return. If sigma is 10%, stock is relatively stable. If sigma is 50%, stock is extremely risky. Uh, Deep quant finance understanding is the progression which we have seen from, let's say, slide 11 to 20, right? It's actually the roadmap of modern derivative pricing. First, we understood the random variable. Random variable took us to distribution, then PDF, then CDF, then expectation, then variance. Then we go to risk neutral probabilities, then we go to option pricing, right? So by the time you reach stochastic calculus, Ito's lemma, GBM, Black-Scholes, Monte Carlo, VAR, expected shortfall, or even machine learning finance, you are repeatedly using the concepts which are introduced in these last 10 slides. These are not the basic statistics topic. You're doing the mathematical language of quant finance, right? So please understand a random variable leads to distributions, that leads to PDF, that leads to CDF, that leads to expectation, to variance, to risk neutral probabilities, to the option pricing. Okay. So this is what we need to understand is the most common measure of volatility, so higher variance, more uncertainty, higher risk. Variance standard deviation, quantify risk by measuring how widely outcomes vary from the mean, right? So that is what we have. Then we go to question number, or then we go to your slide number 21. Your mean variance framework in portfolio optimization. This slide is the birth of modern portfolio theory. Everything started with Harry Markowitz in the 1950s. Before Markowitz, investors focused solely on your return. Markowitz asked why look only a return, why not consider risk too? This idea won him a Nobel Prize. The two numbers that matter is that the slide says investor compare portfolio using your expected return, reward, how much money you expect to earn, right? Variance, standard deviation is how uncertain the return is. So this is what need to be understood when we are trying to uh, do your expected return and your variance, right? So this is the basic idea which Markowitz kind of gave us, right? So if you have to evaluate the expected return of portfolio, we have to take portfolio weights, we have to take mu expected return vector. When we have to take a portfolio variance, we have to take covariance matrix of asset return. Very, very important. If you have to do optimization, maximize your expected return for a given risk level, again, a concept which was made popular by Markowitz, right? He highlighted that by it is very, very important that all these things, right, be understood in terms of your covariance metrics, optimization, and all those things. Because if you don't understand them mathematically, right, you cannot actually solve them or scale them, right? Rather, you can still solve them, but you cannot scale them at a bigger level, at a desk level, at a bank level, at an institution level, when there are thousands of probabilities, thousands of trades, or millions of probabilities, or millions of trades which are going simultaneously, right? So you cannot do that. So that is very important to understand, right? And or minimize risk for a target run. So optimization, both of these lines are same, right? Maximize the expected return for a given risk level or minimize risk for a target return. Both are kind of same. So we need to understand that, right? And the key takeaway is that mean variance optimization shows why expectation and variance are the two core statistics in finance. And we need to keep in mind both of them, right? So if you are a student of finance, you need to understand this mathematically, right? That's why we are covering it here in your course also, right? So remember that. I think this have been covered multiple times, right? But you need to be very, very clear that how this need to be studied, right? So the two numbers that matter for every kind of investor is expected value of the RP, how much money you expect to earn, variance, standard deviation, variance of RP, how uncertain the return is, portfolio expected return, ERP, looks scary but it's simple, right? It's nothing but the weighted average, right? Probability return is simply a weighted average. Similarly, portfolio variance, the formula looks scary. It's one of the most important formula in finance. Notice expected return needs only mu, risk needs the covariance metrics. Why risk harder? Because expected return only looks at individual asset. Risk also looks at how assets interact, how they move together, diversification effects. This interaction is inside your covariance metrics, optimization problem. Investor want maximum return for a given risk or minimum risk for a target return. This creates the famous efficient frontier. Every quantitative portfolio manager, hedge fund, venture fund, sovereign wealth fund uses some variation of this framework, right? We need to keep in mind. So that is very important to understand. Okay. All right. Next is your linearity of expectation. This is one of the most beautiful results of probability. We are saying that the expected value of ax plus by is equal to a expected value of x, b expected value of y, expectation distributed through addition. Amazing fact, this does not require independence. Most students incorrectly think independence is needed. It is not. Example, suppose ex is equal to 10 and ey is equal to 20, then ex plus y is equal to 30, always true. Finance interpretation is suppose portfolio return RP is equal to 0.6 R1 plus your zero point 0.4 R2, therefore ERP, right? ERP is nothing but your 0.6 ER1 plus 0.4 ER2. Simple. This is why expected return are easy to compute even for portfolio containing thousands of assets. So why is this powerful? Because expected return scale perfectly. Double position, expected profit doubles. Triple position, expected profit triples. This does not behave this way. This is why expectation is linear, but variance is not. Right? So please keep that in mind, right? Very, very important, guys. Now, portfolio example, same thing I've already given you. Also, the slides applies linearity directly. RP is equal to W1 R1 plus W2 R2 plus WN RN. Expected return value also given here. Vector form, we understand this very, very well. This compact notation is everywhere. Portfolio theory, kappa and factor models, back determinant disparity. Intuition portfolio, expected return simply weighted average expected return, nothing more. Uh, Weight is given, return is given, portfolio return is given 9.4%. Important observation, expected return equals diversification. This does not, this becomes crucial in the next slide. Right, W is the weight vector, mu is the expected return vector. Interpretation is portfolio expected return is weighted average, doubling an allocation, double contribution to expected return. Key takeaway, portfolio expected return is easy. It's just the weighted sum of individual expected return, right? So this is what you have, right? Then we have covariances, how two variables move together. Again, this slide is one of the most important portfolio management. We are trying to understand your covariance of x and y is nothing but expected value of x minus expected value of x, y minus expected value of y, and taking the combined expected value. Covariance measure whether two variables move together. Positive covariance when X rises, Y tends to rise. When X falls, Y tends to fall. Example, bank stock, HDFC, ICICI often move together, not necessarily, but often. Positive covariance, negative covariance, covariance XY. Right, we have simple idea. One rises, other false. Example, historically, stock gold sometimes show negative covariance during crisis. Zero covariance, covariance XY. Zero, no meaningful linear relationship. Why does finance care? Good diversification comes from covariance, not from expected return, not from variance. Covariance, example, two risky stocks, each volatility 20% is perfectly correlated. Portfolio stocks or portfolio risk remains high. Negative correlated portfolio risk collapse dramatically. Massive insight here is diversification is mathematically a covariance story. This is why portfolio manager obsess over correlation metrics, right? So keep that in mind. Okay, fine. Then we get into the next part, which is correlation. Correlation, standardized covariance lie between -1 and 1. Covariance is a problem. It depends on unit. Correlation fixes that. Formula is given here, right? Everything is given. Correlation, standardized covariance result is -1 and 1 lies between that. Always interpretation +1 perfect positive relationship as I move together, -1 perfect negative relationship as I move opposite. Zero, no linear relationship, important exam trap. Correlation is zero does not imply independence. There may still be non-linear dependence. This become important later in popular and advanced model. Why correlation popular? Because it is unit free. You can compare equities, bond, commodities, currency using the same scale. Right? This is what we have. Why correlation is used in finance, comparable across asset, drives multi-asset portfolio and risk model behavior. Key takeaway, correlation is the most common practical measure of dependence using portfolio risk and hedging, right? So that is what we have. Okay, fine. So again, now portfolio risk depends on your covariance and correlation. Slide explained why diversification works. Right, for portfolio of an asset, the covariance relationship are collected into covariance metrics. This portfolio variance, such and such. Uh, if you look at diagonal elements, which give us variance of diagonal elements, covariance, portfolio variance, you understand is the central portfolio risk equation where this key insight, expected return, ERP is equal to your weighted average, depends on your return, risk is equal to weighted average, but depends on covariance, also depends on relationship among assets, diversification lodges, highly correlated asset, two airline stock, two bank stocks, two tech stock. Risk reduction is weak. Low correlation assets, stock plus bond, stock plus gold, risk reduction improves. Negative correlation, maximum diversification, potentially huge risk reduction. Risk management connection, war model, expected shortfalls, risk testing, risk parity, factor investing, all rely heavily on covariance matrices, which we need to keep in mind. If assets are highly correlated, diversification is weak. If assets are low or negative correlation, portfolio risk reduces strongly. Risk management application, depend heavily on correlation and covariance estimates. Key takeaway, expected return adds linearly, but risk depends on core asset covariance structure. Okay, so this is good. Then we get into your key takeaways, random variables, and risk modeling. Please understand this slide ties to kind of ties everything together, right? Discrete, random variables, countable outcomes, example, default or no default, number of claims, number of trade, described as Px is equal to X. PMF, continuous random variable, which is this. Infinite outcomes, example, returns, interest rate, FX rate, described by FX, which is PDF, right? Probability of interval, which is given, right, in this formula, this simply area under the curve, right? CDF is given by this, right, which is in accumulated probability used extensively in war, Black-Scholes, credit risk. Key takeaway, random variables and distribution from the core language of your quantitative finance. We need to understand very, very clearly. Random variables are essential tools for modeling uncertainty and risk. They represent uncertain outcomes, the return, prices, rates, and defaults. Understand discrete, continuous CDF, etc. Okay. Then we get into the next part, which is your summary of the expectation of the risk measure and the portfolio dependence. Complete map of quantitative finance. Expectation measures your reward. Right, variance measures your uncertainty. The formula is given. Standard deviation is the root of variance. Linearity makes portfolio return calculation easy. Covariance measures the co-movement. Correlation measures the standardized dependence. The bigger picture here is that the last 8 or 10 slides are actually introducing the entire logic behind your Markowitz portfolio theory, your efficient frontier, your CAPM, your multi-factor model, your risk parity, your war and expected shortfall, your black Litterman, quantitative asset management, The chain is expected return leads to variance, covariance, correlation, portfolio risk, portfolio optimization. Once you understand this chain deeply, you understand why a portfolio manager spends more time studying covariance matrices than studying individual stock returns in professional portfolio management. The real edge often comes not from predicting returns, but from understanding dependence, correlation, diversification better than everyone else, right? So that's what we need to understand. Fine. All right. With that, we go to the practice question, guys. We need to understand that. So the first question we have, right? So here, a stock return R has distribution which is given, R and the probabilities are given. So it is very easy, right? So you multiply expected return you to find out minus 0.10 into your 0.2, 0.05 into your 0.5, 0.20 into 0.3. To solve it, it gives you 6.5%. Financial meaning is that expected return represents average long-term gain, right? So it is just multiplication of these things, nothing else. Just focus on understanding. Simple question. Next question here we have what we need to know is using your expected return mu is equal to 0.065. Find your again variance, right? So this value you have to figure out. So what will happen here? Same earlier thing 0.2 minus 0.10 minus 0.065. This was the mean value. So square it 0.5, 0.05 minus 0.065, square it 0.3, 0.20 minus 0.065, square it. If you solve it, 0.01025. Okay, financial meaning variance measures your investment risk, right? So we need to keep in mind. Question number 3, probability under your normal return distribution, we need to figure out. Now, this probability under normal return distribution, your Z is equal to your 0 minus 0.08. This is the mean divided by your sigma 0.04 comes minus 2. So I have to find probability of Z less than minus 2, right? Which will come from your Z table. Probability loss, we have to find out from the Z table. Using VAR calculation, the value is 0.0228, right? Which is probability of loss is 2.28% using VAR calculation. This will come from Z table value, guys. This is Z table which we use. Okay. Then we have your question number 4, expected payoff. Value is 120, 80, probability 0.6, 0.4, strike is K. You find the expected value. So max of 120 minus 100, comma 0 equal 20. Max of 80 minus 100, comma 0 equal to 0. So 0.6 into your 20 plus 0.4 into 0 equal to 12. Right. So option value depends on expected payoff unless under your risk neutral measure, right? So that is what we are trying to figure out. Last but not the least, question number 5 now. Question number 5, basically two assets are given, sigma 1, sigma 2 are given, correlation is given. So we know sigma square P equal to sigma 1 square. We have to take W1 square. Sigma 2 square, we have to take W2 square. 32, W1, W2, correlation, sigma 1, sigma 2. Right, so we put the values 0.25 into 0.04 plus 0.25 into 0.0225, 2 into 0.25 into 0.5 into 0.2, 0.15. Right, we do that. and we get 0.023125, right? So this is what we get. Diversification reduces your risk. That's why we are calculating the portfolio variance here. Okay. So that is what you need to know. Pretty straightforward, pretty easy, guys. So this is done, guys. Question number 6 is answer is here, 7 is here, 8 is here, 9 is here, and 10th answer is also here, right? With this, we have completed this chapter, guys. A little longer, but not so difficult. Go back, understand the concept. You need to understand your PDF, your CDF, probability density function, probability mass function, your cumulative distribution function. You know, you have to understand that, right? So expected values have to be understood, right? These 5 questions are obviously important, but if you uh, kind of focus on the summary, right? So you see here, we understood covariance, we understood correlation, we understood linearity, right? How it affects the returns, right? Standard deviation is a volatility. Standard deviation is a volatility metric. Variance, we found out. Expected value, we found out, and we focus on your CDF, cumulative distribution, cumulative probability up to a threshold, and discrete random variable, continuous random variable, how the formula differs, where they are used, where they're not used, uh, different vector forms, different formulas, uh, continuous, discrete, expectation, CDF matters in finance, for continuous, discrete, random variable, probability below threshold, log normal for stock, probabilities under area under the curve, continuous random variables, PMF, PDF, binomial random event, success counts, discrete random variable, continuous random variable, right? So go back, revise it, guys. Very, very important. With this, we have completed this topic. I'll see you in the next topic. Okay. All right, guys. Thank you.